Okay, so everything's good. So today is very nice to have Aldo Cotrone from the University of Firenze, Florence. He will tell us about holographic QCD and gravitational waves. So please, Aldo, whenever, go ahead.
Okay. Thank you for being here, and thanks to the organizers for giving me the opportunity of giving this talk. The talk is going to be, can you see the arrow? Sorry. The pointer.
Move it? Yeah, we can.
Okay, very good. The talk is going to be split in basically two parts. In the first part, I will give a brief overview of the holographic QCD model, or the Sakai-Sugimoto or Witten Sakai-Sugimoto model. And in the second part of the talk, I will use this model for a very specific task, that is the study of possible signals of gravitational waves. The second part of the talk is based on two papers. One is already out, and the other one is going to appear hopefully very soon, that I did in collaboration with Francesco Bigazzi, Alessio Caddeo, and Florence University, very good PhD student, and Angel Paredes. So this is the plan. I will, of course, the subject of the Witten Sakai-Sugimoto model is a huge subject with many applications. So it's not possible to give an overview of all the applications. So I choose to give an introduction to the very basic of the model, mention some extensions, and in particular, we will spend a couple of slides on the description of the baryons in the model and on the confined phase of the model. And this was for the first part of the talk. And then in the second part, I will first tell you what type of gravitational waves I will focus on, just to do the cosmological phase transition. The idea is to use, of course, the holographic theory as a dark sector, and to study possible gravitational wave signal from phase transitions in this dark sector. Okay. But let me start with the review of the Sakai-Sugimoto model, well, the holographic QCD model. And since this holographic QCD model has a pure glue part, let's start from holographic YAMLs, actually. So the theory that was put forward by Witten in the early days of the holographic correspondence. It is a theory which is living in the Ward volume of NC D4 branes, type 2A, and these D4 branes are wrapped in a circle with antiperiodic boundary conditions for fermions. This condition breaks supersymmetry and give mass to the scalar, so that at low and very low energy, you're left with pure non-supersymmetric 4-dimensional SUN YAMLs, and then with all the towers of Kaluza-Klein modes, all the other massive modes. Okay. The interest in this theory is, of course, that there is a dual holographic description of the theory, which includes a dilaton for form Ramo-Ramo field strength, which I didn't write. I just wrote the metric, which is this one here, which is the important part, let's say. We have a 4 Minkowski direction, this one. The radial direction is called U for a historical reason. This is what we used to call it typically in Witten's theory. And there is a 4 sphere, but the important part of the metric is formed by the radial direction and this circle, the x, which is parameterized by the coordinate x4, which together with the radial direction has a topology of a cigar. So it is a smooth manifold, and the geometry ends smoothly at the tip of the cigar at this position U0, which is a parameter of the model. Different from 0, such that, as you can see, the TT component, also the XX component of the matrix, at the end of the space in the deep, what's the deep infrared in the dual field theory, GTT is different from zero, and as you know, this is a signal that the dual field theory has confinement and mass gap, in this case, for the glue balls. The confinement, what I mean is that the Wilson loop exhibits an area law, and this can be understood by the fact that the fundamental strings reaching the bottom of the space, almost the bottom of the space, has a finite tension because of this condition. And the mass gap is due to the fact that when you solve for the fluctuation of the gravity modes, this condition forces you to have a discrete spectra without a massless mode. So you have a mass gap for the glue balls. The dual description, the dual holographic description based on this solution is valid as usual in the planar limit, so the number of colors is large, at large toothed coupling. And unfortunately, well, as in all basically holographic models, in this regime of parameter, the theory doesn't describe pure EM mills because the mass scale of the Kaluza-Klein modes coincide with the mass scale of the glue ball. So they are not decoupled. So the theory is quite similar to pure EM mills, but has many degrees of freedom, more than pure EM mills. This parameter U0 finally is what sets the dynamical generated scale lambda EM mills, which in this theory is typically called MKK. So I'm going to use this form of calling, this way of calling the dynamical scale, MKK. Okay. So holographic QCD is based on that background, but with some D-branes supporting flavored degrees of freedom. The idea of Sakai-Sugimoto was to use D8 and anti-D8 branes. The reason for this is that if you study the spectrum of the strain connecting D4 branes to D8 branes, they are put in certain configuration. They are not parallel. So in the spectrum at low energy, there are just chiral quarks. And so you have the correct spectrum for a theory which resembles QCD. The D8 brane has a codimension 1, so the codimension is taken to be on the cigar, as you can see in this picture. So at infinity, the D8 branes look like a point on the circle, and the anti-D8 branes also look like points on the circle. So here I'm studying the simplest configuration where the D8 and anti-D8 branes are placed at antipodal points on the circle. You can also place them in different configurations. So in the ultraviolet, let's say you have two separate stacks of D8 and anti-D8 branes. So the favor symmetry is UNF times UNF. But then you have to study the solution for the embedding of these D8 branes into this geometry, okay, this width and background. So you write down the dBi action. Here, the embedding is parameterized as x4 as a function of the radial variable u. And the equation of motion is this one as only solution, in this case, the one in which the D8 and anti-D8 branes actually join in a smooth way at the tip of the cigar. So you just have really one stack of branes. So if you had so what is the UNF times UNF symmetry in the ultraviolet is actually broken to the diagonal UNF symmetry. And that's the very nice geometric realization of chiral symmetry breaking in the Sakai-Sugimoto model. So the model is non-supersymmetric, confinement, and has a mass gap, has the correct degrees of freedom for a theory which mimics QCD, and also the correct pattern of symmetry breaking. As usual, from the low energy modes on the D8 branes, you can read the spectrum of mesons, for example, from studying the small fluctuation of the embedding of the D8 branes and the gauge fields of the D8 branes. And as we will see briefly, instantonic configuration for the gauge fields on the D8 branes allow you to describe baryons in the low energy limit. So let me start from the mesonic sector. I'm going to just to describe the gauge degrees of freedom on the D8 branes, which I'm going to use the curly F notation. So this is the dBi action. On the if you expand it at first non-trivial order on the witness background and integrate on the fourth sphere, you are left with this 5-dimensional action. Okay. Here I'm using a different notation for the radial direction. So I pass to this ZY coordinates on the cigar. So this is basically the cigar as topology of a disk. This is a convenient set of coordinates because the D8 branes are along the Z direction at Y equals 0. Okay, and the Z direction is basically the holographic radial direction. Okay. So the 5-dimensional action is composed by these two pieces. And then what you can do is, let's concentrate on just one flavor brane, so one flavor. If you can expand in mode the Z and mu component of the gauge fields in a complete normalized set, this phi n and psi n, and put this expansion back in the 5-dimensional action, integrating Z, and what you're left is a 4-dimensional effective action for, you see, a tower, an infinite tower of vector mesons, which are massive. The masses are set by solving the equation of motion for these modes, psi n, which is this one with certain eigenvalues lambda n, and the masses are, of course, proportional to the dynamical scale of the theory. There are a tower of, if you can study also parity, and there are tower of vector and axial vector meson, which in QCD you would call the row mesons A1 and so on and so forth. Okay. And then on top of this tower of vector meson, you discover a scalar which is massless, this phi 0. You see, there is no mass term for it. And actually, it is a pseudo-scalar, which is naturally identified with the goldstone of this chiral symmetry breaking, which we saw here in this slide. Okay. So the theory has a mass gap apart from the goldstone of the symmetry, the flavor symmetry. Okay. So this is very nice. You can also study the extension to many flavors. In this case, you can define a pion matrix. This is a standard pion matrix. And holographically, you can write it in this way as an exponential of the Z component of the gauge field. F pi is a constant, which is known as the pion decay constant. So if you define this matrix U, now this gauge field F mu Z and F mu nu can be written in this way, such that this 5-dimensional action reduces to this, well, this is the Lagrangian, this effective Lagrangian in 4 dimensions. And this effective Lagrangian is nothing else than the chiral Lagrangian, this first piece, plus a Skirm term. The Skirm term, well, the chiral Lagrangian is the low energy Lagrangian that you postulate in QCD in order to study the pions, basically, the physics of the pions, which dominate the low energy physics of QCD. And the Skirm term is the one that allows you to describe baryons in this low energy Lagrangian as solitons of this pionic field U. So you get precisely from the Sakai-Sugimoto model, you get precisely what you expect in QCD. And the point that I would like to emphasize is that not only you get what you expect in QCD, but you don't have to postulate it as we do in QCD, because in this case, in the holographic theory, you are able to derive these Lagrangians from the gravitational degrees of freedom. Okay, so this is not peculiar to the Sakai-Sugimoto model. It is true also in other holographic models, but it's a very nice feature of this of the holographic construction. So, as I told you, yes.
Can you hear me?
Yes.
Ah, okay. So this screen term also you also get it from just DBI.
Yes. Yes. This is the piece. So you get from this piece of the action.
Okay.
Okay. Then, of course, I'm here in the list. I didn't say anything about the Chern-Simons term of the deviate brain, but they play a role. Of course, you can study also that piece of the axiom. They give the best Zumino-Witten term, so you can study a chiral anomaly of the theory, which is exactly the same as the one of QCD. You can get the Witten-Veneziano formula for the mass of the eta prime in the model. So this is a list of the first extension of the first topics that you can study within the model, which of course I don't have the time to give to enter into any details apart from the last 2 points. But I wanted to show you, to flash an incomplete list of the topics that you can study, to give you an idea of the fact that this Witten Sakai-Sugimoto model reproduces really a huge number of aspects of low energy QCD. Okay. So actually, the first thing that you can do is to add vector mesons to this effective Lagrangian. You can study also interaction among these mesons and discover that the theory exhibits vector meson dominance. You can also add a small quark mass, because up to now the quarks have been considered to be massless. And when you discover, for example, that you have the Gomorrah relation realized in the model. When you add the quark mass, you can study the physics of the theta angle. This is an aspect in which I've been involved in the past few years. Also study the theory at finite baryon density. And let me tell you that the one that you can get from the gravity modes, this one are a part, of course, of the full mesonic spectrum. Many more meson you can get in the model if you study the spectrum of open strings attached to the deviate brains. And so you can feel a certain gap between the spectrum of the model and the spectrum of the mesons in the particle data book. Okay. So before okay, in this list there are baryons and the deconfinement phase of the theory, but before going to describe how baryons are described in the model, I will describe first the baryons, because then the table include both baryons and mesons. So sorry about that. The baryons have as usual, two possible point of view in which you can study baryons in the model, which I call microscopic and macroscopic. The microscopic point of view is the original one, due by Witten for ADS 5 times S5, but it's exactly the same in this model. You can describe a baryon vertex by taking a D4 brane and wrapping it on the 4th sphere of the geometry. Okay. This is the action, so you get a certain mass, which is precisely scales as the number of colors as you expect for a baryonic particle, and of course the mass is set by the dynamically generated scale. Why is this baryonic vertex? Well, you have on the fourth sphere, you have a flux of the four form, the Ramon-Ramon four form. So the flux is nowhere to go because the fourth sphere is compact. So you have to attach NC fundamental string in order to suck up the flux. Okay? And then the other side of these strings can be attached to the D8 brane, and this is a precise configuration of a baryon. So you have NC quarks which join at the baryon vertex. Okay. This is a kind of the original way in which baryon vertex was described, but it has not been employed for a long time, at least in this model, apart from some paper by Sakai-Sugimoto, and recently this point of view has been employed again in order to study spectra of excited baryons by considering the excitation of these open strings. The point of view which has been used more in the past on the baryons in this model is this macroscopic point of view, where these D4 branes here in this picture, this is the baryon vertex, this VAP D4 brane and the D8. But as you can see, you can put the D8 D4 onto the D8, and it is the dissolved D4 on the Ward volume of the D8. So you should be able to describe it in terms of the low energy modes on the Ward volume of the D8 branes. And in fact, you can describe this configuration as an instanton on the Ward volume of the D8 brane. Let's consider the two number of flavors. What is the instanton I'm considering? Well, this gentleman we're considering. Well, it's actually the standard BPSTS instanton in this 4 directions. So in the 3 Minkowski spatial direction plus the holographic direction. This is an instanton in this direction, so it looks like a point particle in Minkowski. So this is the solution, the explicit solution. Here you can write down explicitly the pion matrix corresponding to the solution. So this is the skirmion, if you want, in this language. And you can study a number of things from this description. As the first thing, you can study the energy of this configuration. You find out that the energy of this low-lying configuration coincides with this picture here. Then you can study the whole spectrum of baryons by quantizing. You see the instanton has a certain number of moduli. Some of them are pseudo-moduli in this model, but this is the rho, for example, is the instanton size. You have the position, x and z. And also you have the SU2, in this case, moduli, which I call A. So in quantizing this moduli, you find out a whole spectrum of other baryons that you can compare with the phenomenology. And you can extract also then, when you have these baryon states in N, you can construct a lot of observables, for example, radii, couplings, and so on and so forth. Just, for example, by taking the web of flavor currents, and which is the point of view employed in order to construct this table. So in this slide, what I wanted to do is to give you my opinion on a question that it's a natural question that comes to mind when dealing a bit with the model. That is, how well does the Witt and Sakai-Sugimoto model perform from a quantitative point of view? Because I hope it's clear, it has been clear from what I've been telling so far, that the model is very nice in geometrizing and reproducing holographically really a lot of qualitative features of QCD or low energy QCD. And let me tell you, there are also some qualitative things that you cannot study in QCD and you can study in this model. Okay, I'm not going to enter into the detail, but you have also extra bonus stuff from the model, from a qualitative point of view. But you can also ask what about the numbers? What about the spectra? What about the couplings that I can, all the observable that I can calculate in the model? Do they perform well when I compare this with the phenomenology? And so here I reported two tables of numbers. The first one is the meson masses, and the second one is some nucleon properties that you can study with this description. And let me consider these meson masses. So this column is the prediction of the model, and this one is the experimental values. The mass of the raw meson is taken to fix the parameters of the models. And as you can see, the first few mesonic masses are in good agreement with the experimental values. But as you move towards higher mesonic masses, you start deviating from what you find in the particle data book. And this gets worse and worse as you go on with energy, with the masses. Okay. And basically the same thing happens with all the sectors of the theory, also in the for what concerns the nucleon properties, with some differences also for the nucleons. For example, the mass spectrum of the nucleon is not so good, but there are other observable which come out quite well. For example, here you have the mean square radius of the nucleons. As you see, the number is not very different from experiment, and is better than what you get from the Skirm model. Okay. But for example, for the electric radius, the model gives 0, which is in a sense close to the experimental value, which is small. It's closer for sure than the Skirm prediction, but it's not exactly the same. Okay. So also in this case, there are numbers which are close to the experimental value, but you cannot trust the numbers to be faithful, to faithfully reproduce the experimental values, as long as you go up with the energy. So my point of view is basically in this sentence, from a qualitative point of view, the model gives you, sorry, from the quantitative point of view, gives reasonable agreement with the experiments, only if you stick to the infrared part of the theory. This means that if you are studying some observable for which you have the lattice in your hand, you're done. You can consider at all the Witt and Sakai-Sugimoto model, because it cannot compete. But for other observables for which you cannot use directly lattice, the model is as good as all the other, or maybe sometimes it performs better than other effective field theory description of low energy QCD. Okay. So this is my view on what we can get from the model. So let me spend a few words, 2 slides on the confined phase. As a first thing, here I have a description of the confined phase, the pure gauge part, so there are no flavor brains around. A solution which has the same ultraviolet asymptotic as the first one that I show you is the D4 black brain solution, is this one. As you can see, that the only difference is that this function F, instead of being in front of the circle, is in front, is the blackening factor. Okay. So what was before the cigar now is a cylinder. It ends at the position UT, which is the position of the horizon. Okay. At the horizon, the GTT component of the metric is 0 automatically, and this is a signal of confinement, for example. The fundamental string is 0 tension. And this parameter UT sets the temperature scale of the theory. When you compare the free energies of this theory and of this background and the previous one, you find out that the transition is first order. It happens at a temperature which, not surprisingly, is proportional up to some pi's to the dynamical generated scale MKK, and this is the confinement transition. Okay, so this is a first of the two first-order transitions that I'm going to show you. What about flavors? Well, for the flavors, there is this interesting stuff that you can have in this model chiral symmetry breaking also in the deconfined phase. So in principle, the two phase transition, so confinement, deconfinement, and chiral symmetry breaking and restoration can be separated in the model. It depends on where we place the ending point of the D8 branes. So if we consider the configuration in which the D8 branes are antipodal on the circle at infinity, then the two transitions coincide. That is, in the deconfined phase, you have just this configuration where the two stacks of the D8 and anti-D8 branes are separated and fall independently into the horizon. So you have a chiral symmetry restoration, just that configuration. But if the branes, the endpoint of the branes are closer, sufficiently close, it can be that the preferred configuration is the one depicted here on the left at fixed temperature, of course. And so this is a connected configuration. Okay, so you have chiral symmetry breaking, but in the deconfined phase. So in this case, of course, when you rise the temperature at a certain point, you reach a second critical temperature in which the preferred configuration is no more this connected one, but it's the disconnected one. So you have this chiral symmetry restoration transition, but which is separated from the confinement transition, okay? And it happens at this other different energy scale, which here I'm calling Fk, which is set basically by the position of the tip of the D8 branes, okay? And also this transition is a first order transition, okay, because it's a competition between these two configurations for the D8 branes, okay. So this is basically concluding the first part, the review of the Sakai-Sugimoto model, and then in the second part, I'm going to use this model for what concerns the gravitational waves. So it's a good point to stop to see if there are questions.
Yeah, as I said before, whomever wants to ask a question, just go ahead. I had a small one, if nobody else. So when you this comment on the how the masses of the tower fail for higher excitations and the formations, for instance, this is this thing that the mass scales instead of quadratically linear with the number deck.
Yes, yes, of course.
There's no way out in this model of
no,
I'm asking.
No, I mean, in this model, in the top-down models, for example,
yeah,
there
exactly.
are no way. All of them behave the same. You see, the ultraviolet completion, the ultraviolet of the theory is in this specific model is completely different from QCD. You just have all these tower of Karuza-Klein modes, then the fifth dimension completely opens up. And then if you go even further in the ultraviolet, you have a little string theory completion. But anyway, apart from this fact that the ultraviolet is completely different from QCD in all top-down models, how the mass scale with N is different from what you expect in QCD. Okay.
Yeah,
that's true.
Thanks.
Okay, so the second part of the talk, first of all, let me apologize if you already saw this part of the talk, because I already gave it. But it's about gravitational waves. And here I wrote a resume of what I'm going to say, to tell you in this in the second part of the talk. So these are the main points, if you want to just to catch the punchline. The content is the following. As you know very well, now we are in an era where we can do direct measure of gravitational wave signals. There are experiments going on which already detected gravitational waves, and there are a number of experiments which are being built or in the study phase in these days. So here, for example, I have a plot of the Zohr experimental sensitivity curves. This is the plot of the power spectrum of the gravitational waves as a function of the frequency of the waves. And these are the sensitivity curves for different experiments. The shaded ones are the ones which are active. So we are taking data in these parts. This is LIGO, Virgo, and Cagra now. And these are pulsar timing array experiments. And the other ones are experiments which are under construction or have been proposed. Well, there are some of them which are at a very good point. For example, LISA is going to be launched for sure. So the type of experiments are either pulsar timing arrays or interferometers, which are this LISA and BBO and the SIGO, for example, are space based interferometers. And here in this zone, there are the ground-based interferometer as LIGO. Okay. As you can see here, on top of improving a lot the sensitivities in the following years, these experiments will scan a huge window in frequency of the gravitational waves that will be potentially detected. And so it's a very good, it's very important for theoreticians to explore what types of gravitational waves this experiment can detect. So what are the possible sources of gravitational waves? And one such source of gravitational waves comes from cosmological first-order transition, which generate stochastic backgrounds of gravitational waves. Okay. So unfortunately, if you look at the standard model, there are no true first-order transitions. So you don't expect any spectrum of gravitational waves just from the standard model. But there are a number of beyond the standard model scenarios in which you have some extra sectors, some hidden sector, or I'm going to call it dark sector, because these are sectors which can account for the dark matter. And in these extra sectors of the theory, you can well have a first-order transition. So this is very standard. A lot of dark sectors, which have been studied in the phenomenology, are Yang-Mills or QCD-like theories. Okay. So our point of view was the following: what if this the gauge group of these Yang-Mills or QCD-like theories is sufficiently large, such that the planar approximation is a good approximation? In this case, the theory might even admit faithful holographic description. Right? There is this gap in the masses, for example, of the globules or the spectra. Okay. Or this is one point of view. So there is the possibility that hidden sector can admit holographic description, or maybe they are not faithfully described by some holographic theory, but as we have been done with QCD, for the Sakai-Sugimoto model, you can use holography in order to model the basic features of the strong coupling dynamics of this dark sector. So the main message is that we are going to use the Sakai-Sugimoto model as a prototype theory for a dark sector, strongly interacting dark sector. Okay. And I just show you that the Sakai-Sugimoto model has at least two first-order phase transitions. And these two first-order phase transitions generate gravitational waves, if you consider this model as a dark sector. And what I'm going to show you is that the gravitational wave spectra corresponding to this phase transition for certain ranges of parameters of the model fall into the sensitivity of the next generation experiment. Okay. So this is the main message of this part of the talk. Okay. And now I'm going to go into a few details. So the first thing is to recall you about basically bubbling water. So the fact that if you have a first order transition, you have nucleation of bubble of true vacua. So let me consider it here. I just depicted the potential for a single scalar model, which is this one, which has some energy scale, which I'm going to call nkk, not surprisingly, and it depends on the temperature. So we think about our universe, which is expanding, so it's cooling down, so that this scalar has a critical temperature, no? This critical temperature which is set by the energy scale nkk. And at this critical temperature, the position, well, the two minima of this potential change. No? What was the global minimum becomes a local minimum, and vice versa. So the idea is that you start from a large temperature, larger than the critical temperature. So the universe is in this state, this blue dot, in this true minimum. But then as the universe cools down, this becomes false vacuum, so it's not the true minimum. And so you start producing nucleating bubbles of true vacuum induced by quantum or thermal fluctuations. So you produce bubble of true vacuum in the false vacuum. And the rate of production of bubbles of true vacuum can be expressed by the exponential of the action for the model evaluated on the bubble configuration. Okay. The bubble what is the bubble configuration? Here I'm considering spherical symmetric bubbles. So rho is going to be the radial direction in Minkowski. Actually, I can consider just the Euclidean configuration, but anyway, the bubble is a configuration for the scalar field which interpolates in between the false vacuum at infinity. So you have the bubble, so outside the bubble, very far from the bubble, you're still in the false vacuum. And then instead, inside the bubble, you have a true vacuum, or you are close to the true vacuum. So the bubble configuration interpolates between the two. This is an example of the solution for this potential, which I wrote here. As you can see, at large rho, it goes to negative value, which is this one, the false vacuum. And instead, close to the origin, it goes to a positive value, which is around the true vacuum. Now, after the nucleation, if the bubble is sufficiently large, it starts growing, expanding. Then also the universe is expanding, but typically the rate of nucleation as increases as the temperature goes down. And so there will be some temperature Tn, which is called nucleation temperature, in which the ratio of the rate of nucleation over the Hubble parameter is border 1. In this condition, the bubble can percolate. That is, they meet each other, they fuse and percolate all the space, such that at the end of the day, all the universe is found in the true vacuum. Okay. Now, where are the gravitational waves in this story? Well, the bubble itself, a single bubble itself, doesn't produce gravitational waves since it's spherically symmetric. But then gravitational waves can be produced in at least 3 ways. Here, let's concentrate on this part on the left of this picture, this nice picture from this paper. The bubble, we have 2 bubbles here, which are these thick black lines, which meet at a certain point. Now they collide. So when they collide, you lose, they are fusing each other, so you lose spherical symmetry. And so in the collision, part of the energy of the kinetic energy of the bubble is transmitted to gravitational waves. Okay. So this is one channel of production of gravitational waves in this process. Second channel has to do with the fact that the bubbles are not produced in the vacuum because the universe is filled with a plasma of standard model and possible dark sector, hidden sector particles. Okay, so they are moving in a plasma, so they are exciting sound modes. Here in this picture, we have a shell of rarefaction following the bubble. Okay, in these sound modes, they by themselves, they collide, coming from different bubbles, they collide, and there is a production of gravitational waves as well. And finally, all these processes can induce turbulent motion of the plasma itself, and the turbulence is another source of gravitational waves. Okay. So for cosmological purposes, now it's believed that the second channel, the one from sound waves, is the dominant channel for the production of gravitational waves in cosmological first order transition. So I'm going to focus on that channel in the following. And this is more or less the state of the art of the formula, giving you the power spectrum of the gravitational waves as a function of the frequency in terms of parameters of the model. Here I highlighted in blue the parameters which you have to calculate in the microscopic theory undergoing the first order transition. And once you have calculated them, you can use this formula in order to calculate the spectrum, the power spectrum of the gravitational waves produced in sound wave collisions as a consequence of this first order transition. Okay. Let me just quickly go through these parameters. This beta over h is a very important parameter, is inverse phase transition duration. As you see, it's the derivative of the rate, the nucleation rate. So you have to know the bubble solution in order to calculate this parameter. So you have to know the bubble configuration. This KV is just an efficiency factor. Alpha is basically the strength of the phase transition. And G star is the number of relativistic degrees of freedom. V here is the bubble velocity. This is an extremely difficult parameter to calculate because it involves knowing the dynamics, but it's usually approximated in a certain ways in terms of alpha. And capital S is the spectral shape, so it's going to give you the shape of the spectrum. And it's written in terms of the peak frequency, which also include the information about the temperature of the percolation, at which basically the gravitational waves are produced. Okay. So the point here is that you can use this formula from the literature in your microscopic model. You calculate these parameters if you are able to do it, and so you can extract what is the spectrum of gravitational waves that is produced in the first order transition in your model. Okay, and the idea is to calculate these parameters in the holographic model, the Witt and Sakai-Sugimoto model. Okay, and this is what I'm going to show you. So I already show you well, discuss this slide. First, before telling you how to actually calculate these parameters, let me just quickly tell you that you can use the Witt and Sakai-Sugimoto model in to model many different dark sectors, let's say. For example, you just consider the pure blue theory. So without including the flavor brains, you can model a dark blue ball scenario where the dark matter is composed by blue. Okay, and here, of course, the phase transition we are considering is the confinement transition. But then you can add the flavor brains. So you are considering a dark QCD theory. So if the flavor brains are antipodal, as I told you, the chiral symmetry breaking transition coincide with the confinement deconfinement. So you're studying basically the same phase transition. Or, as we're going to show in the paper that is going to appear, you can model in this way the simplest model of composite axion to Kaplan, Kim, and Choi, and Kim. Okay, so you can include this composite axion model in the holographic from the holographic point of view. In all these cases, the phase transition we are going to consider is the same, is confinement, deconfinement. But then, as I told you, you can also separate the chiral symmetry breaking transition if the branes are not antipodal. So you can consider a dark QCD scenario where the branes, where the confinement, deconfinement transition is separated, so you have two separate phase transition. At higher temperature, you break chiral symmetry, and then at lower temperature, you go to the confinement phase. So you have two different phase transition which generate two bunches of gravitational waves. Okay. Finally, let me mention this other possibility. Last year, we showed how to include in the original Sakai-Sugimoto model QCD axion, which it's a model which is called holographic axion or holo-axion. You just add to your QCD-like theory one extra flavor brane, such that the chiral symmetry breaking of this flavor brane coincide with the Peccei-Quinn transition. The Nambu-Goldstone boson that you get from this brane is the axion. Actually, this was the main motivation, the original motivation to study gravitational waves, because this is one of the few examples of the Peccei-Quinn transition which is first order. And so it was interesting to look at what type of gravitational waves can be generated in this Peccei-Quinn transition. Okay, so basically the message here is that we have two different phase transition with the Sakai-Sugimoto model, and we can generate two different spectra of gravitational waves. So let me quickly tell you how we calculate the parameters that are needed to calculate the spectra. Well, this parameter can be, let me start from the confinement transition. The parameters actually can be divided in two groups. A group like alpha, G star, KV, and so on are basically a thermodynamic in nature, in the sense that if you know the thermodynamics of the theory, you can easily extract these parameters. So this is an easy part from the holographic point of view, because the defining relation of holography allows you to calculate the free energy from the supergravity action, and so extract all the thermodynamic data that you need. So this is it's a straightforward part to do both in the confinement, deconfinement, and chiral symmetry breaking transitions. The difficult part is in the calculation of beta over H and the nucleation temperature and the critical temperature T star. Because in order to do this, you have to know the bubble configuration. Okay. So in principle, for example, for the confinement, deconfinement transition, you should solve for the full 10-dimensional supergravity equation of motion, searching for a bubble configuration, which depends at least on two radial parameters, radial variables, that is the holographic radial variable and the Minkowski radial variable. And you have many fields, so the situation, you have partial differential equation, many fields, and the problem is technically quite challenging. Fortunately, there is a shortcut which gives an effect. You can give an effective description of the phase transition along the lines proposed by Creminelli, Nicolisi, and Rattazzi almost 20 years ago. They proposed this for Randall-Sundrum model, so for ADS, but you can do this exactly the same way with the Sakai-Sugimoto model. What is the idea? The idea is that, okay, we want a bubble configuration is a configuration which interpolates between the confining phase and the deconfining phase, no? Which are described by these two metrics. And if you look at the metrics, you can interpolate between these two metrics by just taking this constant U0 and UT, bringing them, for example, starting from this metric, bringing U0 to 0, then switching on UT, and ending in this background. So basically, the idea is to promote these parameters to fields depending on the Minkowski radial direction rho. joining these two parameters in a single scalar and calculate a potential, a kinetic term for this single scalar, and effectively describe the interpolation between these two backgrounds with this single scalar field. Okay. For what concerns the potential, we follow basically this original work. Let's concentrate just on the UT parameter, this one. So we promote it to a variable which depends on the Minkowski radial direction, okay? And we call it T square, TH square, okay? TH is basically a kind of temperature field. When the temperature field is equal to the actual temperature, actually the black brane geometry is regular, and the free energy can be calculated by this defining relation. And this is the free energy of Witten's model, basically. But then, since this is a field which has a position-dependent value, in general, TH will be different from T. So the geometry corresponding to this field has a conical singularity, because the period of the thermal circle is not 2 pi anymore. And the conical singularity gives an extra contribution to the free energy, as was pointed out in this paper. And you can calculate this extra contribution, for example, by replacing the conical singularity with some smooth manifold, and then taking here, in this case, a spherical cap you used, and then take the radius of the sphere to 0. And you get this extra contribution. And adding these two free energy, you get a potential basically for this field, TH, a potential which is minimized, not surprisingly, at the Hawking temperature T, where the free energy is just the free energy of the theory. So it's a way, basically, an effective way of describing the theory of shell. Okay. What about the kinetic term for this field? Well, this was a piece which was missing in the literature. But it was the idea of, dealing with it was quite easy, because if you consider that UT depends on the radial variable, the Minkowski radial variable rho, and you plug the ansatz, appropriate ansatz in the gravity action, from these terms you get precisely a kinetic term for this field TH. You will get a divergent term, of course, but this is the standard ultraviolet divergence that you get integrating in the holographic direction. And we know how to take care of it by just holographic renormalization. In this case, this can be done, for example, by adding this single counter term. Okay. So with this procedure, you can get a finite answer also for the kinetic term. Okay. You can do the same for the other scalar, U0, which we called MH square. Join TH and MH in the field phi, and this is the actual effective single scalar description of the phase transition. You have a kinetic term, finite kinetic term, and the potential. This potential is, of course, the one that I showed you at the beginning. Okay, so we know how to calculate the bubble solution. I show you an example a few slides ago. If you have the bubble configuration, you can calculate the rate from the exponential of the action evaluated on the bubble configuration, and then this parameter beta over h and t star by knowing the rate. So that you have basically all the parameters that you need to calculate the gravitational wave spectra. Okay. Okay, of course, you can use this procedure that we used for the kinetic term in order to calculate the kinetic term for the Randall-Sundrum case. But let me skip this and get to the results. Okay, so this is an example, are examples of the spectra that you can, for gravitational waves that you can get for specific values of the parameters of the model for the confinement transition. In this case, the parameters are just two. It's MKK and this combination lambda is square of the tooth coupling and the number of colors. Here I use the 3 different colors. So it's blue, green, and red. Let me begin from the red curves in order to show you that you cannot do whatever you want with the model. The red curve corresponds to the composite axion scenario that I flashed you at a certain point. It is a holographic realization of a Kaplan's model of composite axion. So this curve on the left is just a guide to the eye. To the eye is a order of magnitude off from the true minimal curve that you can get. That is the curve for the minimal allowed value for the axion decay constant, which is around 10 to the 8 GeV. So the true curve that you have to look at is this rightmost curve. And as you can see, the frequency, the peak frequency is too high to be detected also in the next generation experiments. So here you have a negative answer. You cannot detect a composite axion which has a holographic origin. Instead, for these other cases, as you can see, the curves fall into the sensitivity of future experiments. The blue curve are curves for dynamical scale relatively slow, which is are values which are suitable for more suitable for dark blue ball scenarios. And as you can see here, this is just one example, but there is a window of parameter space in which the signal can be potentially detected by the next generation pulsar timing array experiments. And the same happens for this other curve, which are intermediate values of the dynamical generated scale, this window. This is suitable to describe a dark QCD scenario. And as you can see, there are values of parameters in which can be detected by LISA, for example, or from the next generation ground-based interferometers like the Einstein telescope. Okay. So the message, let me reiterate the message. Here you have a piece of the parameter space of the model for which the gravitational waves that are produced in the confinement transition can be detected in the following 10 to 20 years. Okay. Now, very quickly, let me tell you, well, yes, I'm already over time, very quickly about the second, the chiral symmetry breaking transition. Here, the goal is to find a configuration which interpolates between the connected and the disconnected configuration. So it's this field X4, which now is a function of the radial variable U and the Minkowski radial direction ρ. In principle, you can solve for this and get the exact bubble, no? But these are nonlinear partial differential equations that you get. So it's numerically very challenging. But fortunately, there is a variational ansatz, which is this one, which works extremely well for these two extremal configuration. And when I say extremely well, it means that here there are a bunch of curves. Each line is basically two curves, one on top of each other, basically. One is the true solution, and the other one is the one with the variational ansatz. So it works extremely well. And then you can use the variational ansatz to find the solution which interpolates between these two configurations. This is an example. You can see this is the radial direction in Minkowski. As you can see at the center of the bubble, you have the connected configuration. And then there is a position of the Minkowski radial direction where you make a transition to the disconnected configuration. So that at infinity, you are left with the disconnected configuration. Okay. So you can calculate the bubble, you can calculate the thermodynamics from the dBi action. So you have all the ingredients to calculate the gravitational wave spectra, and these are just two examples. The red one is again the holographic axion scenario. As you can see, again, the Pechenquic transition generates gravitational waves which you cannot detect in the next generation experiment. And instead here I depicted, okay, there are two curves. The one in blue is just the curve for the confinement transition. Okay, and I choose the parameter such that it falls into the Lisa sensitivity curve. But as you can see, the green one is the sum of the signal that you can get from the confinement and the chiral symmetry breaking transition. And as you can see, the chiral symmetry breaking transition generates a second peak, which, if you're lucky, falls again into the sensitivity of your experiment. So you will have two separate peaks, which would be great because you could distinguish this type of signal from signals from other sources. Okay. So this is basically all I wanted to say. Let me just reiterate the fact that the idea is to use the holographic model to model dark sectors, and the outcome is that there are windows of parameter space in which the gravitational waves produced in this dark sector are potentially detectable from by next generation experiments. And that's all. Thank you very much for your time.
Thanks a lot, Aldo. Very nice talk. So there's a lot of people, so let's hope, let's have some questions. As always, just please directly ask. And don't be shy, because I see there's more people than usual, so there should be questions.
Can I ask a question?
Yes, go ahead.
Okay. I was wondering if we can do the same calculation in the ADS5 short-circuit black hole when we have a Hawking phase transition there. What do you think?
Okay, yes. So in ADS5, basically, well, the original calculation by Creminelli, Nicolis, and Rattazzi was based on the Randall-Sundrum model, where the deconfined phase is the ADS black hole. The confined phase is just, well, the Randall-Sundrum model, so it's a chunk of ADS, but then you have to use the radion field here, which is basically the equivalent of this, field MH, which we include here. Okay. Okay, I don't find it, but it's morally it's the same story, but this field is described in a slightly different way in this Randall-Sundrum setup. Okay. This sorry. Well, this type of models, this type of Randall-Sundrum-like models, have been employed a lot because, well, the radion basically is what makes you depart from also from conformality. Okay. But if you're sufficiently close to conformality, you get gravitational wave spectra, which are potentially detectable.
You know what I mean is that transition between thermal ADS and black hole ADS.
Yes. So you are thinking about global coordinates.
Right.
So your theory is right, living on a four sphere in that case. Okay.
Yeah.
Okay. Yes. I mean, if you have a, for sure, if you have a first order phase transition, you can always do this type of calculation.
This is the main point, yes.
Sorry?
This is the main point, yes. When
Yes, exactly. So yes, you are kind of modeling your dark sector in some specific way, which is in that case is let's say n equal 4 on a 4 sphere. Okay, so you're imagining that your dark sector has this at this 4, but for what concerns the calculation, you can do if you have a first order transition.
But when we consider the confinement phase, we have to consider a wall. We have to put a dilaton in theory. I was wondering if such a dilaton plays the role of this radion or this scalar field that you studied.
I guess that, well, in this case, the field is directly into the geometry, and I guess it will be a field, a component of the geometry, always a component of the geometry. I suspect this, not the dilaton. If you're thinking about thermal ADS, I mean, for in global coordinates.
Okay, thanks.
You're welcome.
More questions?
Hi, yeah, I've got a question as well about your gravitational wave signal spectra plots that you've got there. Do you know what kind of wall speeds and alpha values you're using for that, or you get for plotting them?
I just used the Chapman-Jouguet formula to express the velocity of the bubble in terms of this alpha parameter.
Mm-hmm. Yeah.
This is the simplest, this is the simplest thing that you can do. The matter of determining the velocity is one of the hardest part of the story, and you have to know much better the dynamics of the bubble in order to calculate. And this we didn't even try in the holographic. I know that there are smart people calculating this in other models. The other models are typically quite simpler, and yes, but this would be extremely interesting, of course.
Well, it's just there was a paper that came out a couple of months ago by Heinmarsh and Cutting, where they found for relatively alpha's about 0.3 or higher, and for relatively slow wall speeds that you can get quite a suppression in your gravitational wave signals of up to like a factor of 1,000. So it could reduce the signals and whether they're detectable by the loose emission. You
mean for the because it reduced the duration of the processor?
Yeah, well, I think that it as the bubble walls are proceeding, that it slows them down due to, I think it's like hot droplets of metastable phase are forming in front of them, and when that slows it down, then it has something I can't remember exactly, but I remember that they found that there was some suppression in signal that you would find, which is pretty much true for all bubble wall velocities and alpha values, but particularly noticeable for slow walls and strong transitions.
Okay, I'm not sure that we're speaking about the same suppression, but one thing is that the friction that the bubble feels from the plasma typically reduce the bubble velocity, and this is true. And in order to calculate faithfully this friction, you have to know again more details of the dynamics of the process, which we don't know for this model. The term that the suppression that I was referring to, I'm not sure that you're referring to the same one, but the suppression I was referring to was the observation that the duration of the phase transition of the process due to sound waves seems to be quite shorter than what first was thought. Yeah. And this gives a suppressing factor for this channel, which has been my curves. These curves take into account that suppression factor. In fact, if you don't take into account the suppression factor, the peaks are much higher.
Yeah, I think it's probably a different suppression.
Can you tell me well, maybe after that you can tell me the reference. Okay.
No, come on. I mean, okay. I mean, this is unless you are. If you want me to stop recording or something.
No. Okay.
There's no hurry now. We're in the question session, so people, of course, is always free to leave.
I can put the archive link in the chat.
Okay, very good. Thank you.
And then also, let me say that as usual, I will leave this open like for half an hour, so you can connect again and chat.
Yeah, but I think this specifically came from them doing 3D simulations of bubble collisions, and it's not something that's predicted theoretically, but they found that this suppression came about anyway, and it was quite significant for
But in the sound wave channel, or production of gravitational waves or in the collision, for the collisions. Do you remember this?
No, I can't remember
Okay.
exactly. So. Okay, but thank you anyway.
Thank you.
Well, yeah, we're over time, but please feel free to ask more questions. Let's see. Okay, I might have a small question.
Yes.
I was a bit confused by the bubble configuration for the confinement. So how many scalars? So in principle, you should have an ansatz that interpolates between the black hole and the, sorry,
Yes.
so you take one scalar for like the blackening the temperature and then?
Yes, basically I'm using two parameters are promoted to fields, this U0 and UT. But then I just combine them in a single scalar. I define it, the single scalar phi as minus th for phi negative and plus mh for phi positive, such that the full potential is this one. Okay, because you see this, both of them, both of these parameters are should pass through zero, right? You start from a certain value of U0, then you switch it off, it goes to zero. And then you switch on UT.
Okay.
So from zero. So both of them goes to zero, so you can glue them at zero. And you get, basically, you get this potential, which I depicted here, this one.
When you say you get this potential, but
for the free from the free energy.
Okay. Thanks.
By the way, the previous question convinced me to specify one thing. These formulas that are around for the calculation of gravitational wave spectra are well, very nice piece of works, but there are a lot of work still to do there. So often all the ingredients there are approximation, are based on reasonable, but sometimes unproven assumptions. And as time goes by, people are always improving these types of formulas. But there is let's say a big uncertainties, let's say, in this formula. So the spectra that you see around, including ours, are, in my opinion, to be viewed as order of magnitudes estimates at best.
Any last questions, comments?
I have another question about chiral symmetry breaking phase that you introduced. Can you say something more about this?
You mean about the configuration that we found, or about the phase transition in the Sakai-Sugimoto model?
I mean the part of the phase which is related to chiral symmetry breaking.
Okay, so I guess, okay, from this picture, okay, you can see here we have let me try it from this picture. We have this is basically the cylinder part of the geometry in the deconfined phase. So now I'm assuming that we are in the deconfined phase. So just the geometry has this horizon position UT. Now, if you see, if the configuration, original configuration of the branes, the D8 was antipodal, okay, like in this picture. If you cut this with this picture, let's say, very rough, but let's think that you cut this at a certain horizon, okay, the two branches fall into the horizon. There is no way they can join, okay? So in that case, in this case, when you pass to the deconfined phase, you have two separate stacks. the 8 and anti-the 8 branes. So you are automatically also chiral symmetry restoration.
Okay.
Is that clear?
Yes.
Okay. If instead of having this configuration, you start from the branes which, let's say, are the endpoints are much closer. Okay. So now the branes will join not at the tip of the cigar, but for higher values of the radial position. So that when you include like this,
Okay.
so when you include an horizon, if the temperature is sufficiently small, the horizon is not close to the tip of this branes, and this can make you understand that this configuration is again energetically preferred over this other configuration for sufficiently small temperature. That is, when the horizon is sufficiently far from the tip of this branes. So that you have this configuration with, this is chiral symmetry breaking because the branes are joined, but you are already in the deconfined phase.
Okay.
Now, if you increase the temperature, ideally, let's say, very roughly, the horizon gets closer and closer to the tip of the branes, and at a certain point, it is energetically favorable for the branes to split and fall independently into the horizon. So you have, at this temperature, you have a chiral symmetry restoration. So you have a transition from this configuration to this other configuration. Does this answer the question?
Yes, but you mentioned the solution for this, the shape of these branes, the 8 branes.
Yes.
It was not, actually, it doesn't come from solving the equation of motions, I think.
So these two cases you can get by solving exactly the equation of motion, but maybe this one partly numerically. But this extremal case are you can get the exact solutions. Now for the bubble, which interpolates in this, between these two configurations, you don't want just these two cases. You want a configuration which also depends on the Minkowski radial direction.
Oh, I see.
And that as you go far away from the center of the bubble, passes from this smoothly, from this configuration to this other configuration. Okay. I mean, going, yes, as a function of the Minkowski radial direction. And finding this solution is very challenging. I can assure you, people who try, but, because well, I mean, it's not that it cannot be done, but you have to solve this for this the equation of motion for this action, which is again, these are nonlinear partial differential equations, so it's not that you plug in Mathematica and it gives you the solution. So we've found this other way. Achel found this other way of calculating the solution by a variational ansatz.
Okay.
So this is an approximate solution to the true solution. Okay.
What is the big B?
Oh, so big B is a function. This B and Y0 are function of the Minkowski radial direction, which the two interpolate between the two functions which allow you to interpolate between these two. So for radius equal to 0, the function are the boundary value. The boundary condition, let's say, is that for r equals 0, b and y are such that you are in this configuration, and for r equal to infinity are this other configuration. Okay. The form of the variational ansatz, the choice of the variational ansatz comes from the fact that this ansatz for this two extremal configuration works very well.
Good.
As depicted in this.
Yes, I see. Thank you. Thanks.
You're welcome. So by the way, this is in the paper which is already out. This solution, the bubble solutions. Instead, in the paper which we are writing right now, we calculate the gravitational wave spectra.
Very nice.